Welcome back to this unit on practical aspects. We would like to now go through a typical input script of a DEM simulation. As already announced, we're going to use lights here, and the first input that we have to provide is the simulation style definition. This is most of the time very standard and very similar to the tutorials that you have chosen. Second, we have decided to put our input of particle information, domain information, and on numerical parameters into separate files. Lights allows us to include these separate files in this main script here. Why have we done that? Well, if you look at the parameters that are summarized here, for example, the particle density, the Young's modulus, Poisson ratio, coefficient of restitution, and particle sizes, we might want to reuse this information in other input scripts. So if we put it into a separate file and include it here in an input script, we can also include it into other input scripts. That's the main reason. You see, we have done the same for the domain size parameters. Here you will find the variables min and max in each direction and gravity. You will see that we will reference them here later in the base geometry definition. Last but not least, we have a file that is called params-numerics.in. Here you see we have basic input parameters for the numerical settings of the simulation, and we perform some simple calculations, for example, to calculate the dump frequency, so the number of time steps after which we would like to dump the information to disk. Same as before, we might want to reuse this variable definition in other input scripts, and that's why we have put it into a separate file. Of course, we can also directly define variables in the main input script, and this is what we do here. For the filling phase that we are now interested in, we want to specify the mass rate, the total number of particles, and the injection velocity as already mentioned. Also, we need to decide how long the simulation should take. Therefore, we define here the number of time steps to fill, which are in this case 140,000 time steps, and a time to relax the simulation. So after the insertion is completed, we want to wait for a certain number of time steps that the simulation is kind of equilibrating. So this was already the hardest part, to separate essentially the information, the user input, from the remaining script. The remaining script should be changed only by absolute experts and is essentially reflecting the base setup of a simulation. As you know from the lights training tutorials, if you use that software, we first have to define the base geometry. This consists of defining the domain. Please don't confuse this with walls or boundaries. This is something different. We define here the skin distance and the neighbor search algorithm details. Again, all the details are very nicely documented in the Lights online manual. In the next part, we define the material and interaction parameters. And again, you see, we heavily use this referencing of variables. And the reason again is that we want to avoid redundant input into our Lights scripts. Here we define the walls. As I explained before, we have mesh type of walls. For that we need to first load the mesh into the light simulator. Here we do it twice, and the reason for that is clear. We have a wall that we call cut, and we have an in phase that we call in phase. And in this in phase we will not apply a wall, but we will inject the particles. Here is then the actual wall definition. The walls are called ground walls, and here we reference the cut geometry that we have loaded already here with this fix. Last, I told you we want to have a barrier at the bottom, and here we use the wall run model hertz, tangential history, and you choose to have a primitive wall as indicated by this keyword here. Set plane defines that the barrier has a surface normal that is pointing in the Z direction. The next part is dedicated to the particle size distribution. Here we first define the particle radii that we want to put in. This looks like a stupid calculation, but I mentioned it before. LIGHTS wants us to define particle radii and not the diameters. So that's why we divide here by 2. Here we define the individual particle classes. You see we have 4. And again we reference the particle density and the particle radius here that we have calculated here. Last, we use this fix here to then define the particle size distribution. You see, we specify that this should be number based, and here we have chosen to not use variables, but to put the numbers in by hand. The next command that we use is a group command to define the group NVE group, and then we insert the particles with this fix. Again, note that we have used here this reference to the above defined variable for the injection velocity of the particles, as well as the mass rate and the total number of particles to be injected. Here we define the pair style. Here we then define the time step by again referencing this variable. We include gravity, and then we activate here the integration fix. This is the main integration fix. We then define the computes and the thermo to give feedback to the user of the simulation on where the simulation is currently. We define the dump, we define a print, and then we run the time steps until filling. We then unfix the insertion. This is this fix here. And we then run the simulation until the predefined number of time steps for relaxation. Finally, we write a restart file such that we can load the simulation in the next script. Next, we are ready to start the simulation, and we can do this by using a terminal. You see it here. This is a Windows subshell for Linux using Ubuntu. I just issue the lights command, then this syntax. I hand over the input script in.hopper_fill and confirm with enter, and the simulation is running. Data is dumped now to disk, and in the next video we will load the data and inspect the results. Simulation done.